Hello everybody, this is again Dr. Sergey Sarkisov, and currently I want to discuss with us the Fibonacci numbers and the golden ratio. In fact, the reason I'm considering this topic now is because I was recalling an awesome, interesting geometry problem. Let me show you what that is. There's a cool geometry problem that also has to do with the golden ratio and basically this idea of Fibonacci numbers. So before I tell you Fibonacci numbers and what golden ratio are, let's together solve this cool geometry problem. Let me show you what that is, so you aren't too surprised. Let's take a triangle, right? And I'm gonna make it so that there's an angle like 72 degrees. It's an isosceles triangle. Okay, let's do this. Double mark it, and this is isosceles triangle. Let me do a double. And this is isosceles triangle, so 72 degrees. That means the other angle, symmetrically will also be here 72 degrees. For example, why would one angle be bigger or smaller than the other? Argument of symmetry there, and there are other reasons for it as well, such as the law of sines and so on, right? Anyway, let's say we have 72 degrees, 70 degrees. What's that angle on the top? And actually, we could have been given that angle first. 144, sum of 72 and 72. 180 minus that. Oh, we have angle 36 degrees, right? Everyone, 36 degrees. And actually, if I'm going to be realistic with us, this is going to be a little more like this, right, everyone? 36 is a bigger angle, so let's kind of make it look like it looks. Okay, now, what I recall is wanting to figure out something like what is sine of 36 degrees, for example. Let me show you something really cool. So, this triangle can be divided up a little bit more. Let's do an angle bisector from here. So here we go, angle bisector. Let me actually do this a different color a little bit. So angle bisector. Okay. What does that mean? Angle bisector divides angle exactly equally into 2 equals. So this is going to be, oh, this is 36. And this is also 36 degrees, right? Actually, let's do this. Let's copy this and paste it here and kind of erase that 36 there. Just an idea being that we started here and we're going to get there a little bit nicer to keep it that way, I think. Okay, everyone. So let's say we were there, and let me go back to having this 72 degrees. Okay. In fact, even like that wouldn't have been given. Maybe 36 is all you're given, right? So now we divided and we got 36 degrees, 36 degrees. Now let me tell you something here. Look at this triangle right over here. Let me get a little different, the green color again, green marker. Actually, let me do red marker. So watch this. What I can see here, and hopefully maybe you can too, you see this red triangle? This vertex, and this vertex? Those angles are 36, 72, and, well, the other one has to be 72 degrees, right? And if that's the case, what's happening is that we have two similar triangles. 36, 72, 72, 36, the big one, 72, 72. Now, let's say that this length is 1. Let's call it something, right? Let's actually have that this is 1. So the goal, let's say the problem said, and it's similar, I remember when it asked something like this, the ratio of the sides. So basically, let's say this is the ratios, like x and y, and you want to find y divided by x, right? Let's do an easier version. Let's say this is 1 and this is actually x. Make sense? So we want to find x to 1, solve for x, okay? Given this information, solve for x. And this is basically which is the ratio of bigger to smaller. So that's the biggest thing I want you to see from here. Okay, later on I'll explain why. Sides. Okay. So let's do this. Let me show you. And then because it's x over 1, and that's why I set that equal to 1, the base. So it'll be easier. Just less computational and writing, right? Problem and writing. Anyway, so watch this. What we can do is we can, we have this as 1, and if that's x, right? This is this is x. Let's call this, what are we going to call this? Let's call this side S. Okay, and so everyone, this is going to be 1. What is that, by the way? Do you see what that is actually? Before I say side S, let me show you what we can do. You see right here? This is also X, right, everyone? And what is this? That, everyone, is just like the one at the bottom. This is also one. It's isosceles, right? So is this. This is isosceles triangle. Look at that. Cool, right? Cool, right? So we have that this side, which if total is X, and that's 1, is X minus 1. Okay, now, here's what we're going to do. We're going to talk about the law of sines for a moment, even though we don't even need that. But let me show you, because there's another way. The law of sines would be there if you want to find, for example, sine of 36 degrees, which is an angle we can do. And I'll tell you, people say usually in geometry and trigonometry classes, they say, you know what, you can do angles 15, 30, 45, 22 and a half, it's a half angle formulas, and 67.5, and then, of course, you can do the 30, 60, 90, and 0, and, 45 and all that. But there's 18, 36, 54, and 72, angles like that, multiples of 18, you can also do. It's kind of cool. And then I'll obviously go to 9 and multiples of 9. Anyway, it comes from this, because you think about sine of 36 over sine of 72 will basically be giving you what you want, right? On this, let me actually write this kind of a little note. By law of sines, which we've done earlier in other videos, law of sines, right? We know, sine side over angle. So let's do this. Sine of 72 degrees over x is equal to sine of 36 degrees, right, everyone, over 1. So x is equal to sine of 72 degrees over sine of 36 degrees. And I know I'm going a little quickly here, but this is by the double angle formula. That's double angle formula. You know double angle formula, anyone? 2 sine theta cosine theta. That's what sine 2 theta is. So double angle formula applied here gives you that the top is if you do, it's double 36, so you have 2 sine 36 degrees cosine 36 degrees all over this sine of 36 degrees. And so actually, you see what happens is that cosine of 36 degrees is actually what? 1/2 x. So if we find x, we can even find cosine 36 degrees, right? So the goal is, I just want to let you know, so if we find x, we find a representation. There are multiple representations, but this is a representation of cosine of 36 degrees. And then, of course, you can do others like sine and so on, all the functions. So that's cool, which is neat. It's cool. Okay, anyway, let's go ahead and do this. This is really, x is not that difficult to find. Let me show you. Similar triangles, right? So let's do this. Let's do base to the big side. So the base of the little, you see this triangle right here? Let's copy and paste it one more time so you can see it better. Let's take this. Let's go over here. This is really cool. Actually, I haven't done this problem in a long time. I like sometimes doing videos without preparing for them. You can see definitely I didn't do anything besides just knew what I kind of wanted to talk about. So, and this is a long time ago I've done this. But I like to show you the reality of it. Not like I'm just having a prepared lecture for exactly what I'm going to show you, but kind of like, here's what I'm thinking, here's what I'm doing, here are my struggles, here's where I'm slowing down, here's where I'm speeding up, here's where I'm getting excited. Math is, it's almost like it is a science, it is an art, and it's also like, imagine like I'm thinking like dancing, and you're like problem solving, you're doing magic here and there, you're struggling here and there, you're stumbling here and there, you're turning and twisting and double spins and all that. Like I'm thinking like salsa here and there, singing, writing music and so on. Anyway, watch this. So the blue and the red triangle, and the red triangle, I mean this whole big red triangle, right? So what happens is they're similar, right? So by similar triangles, what we can do is, let's just get a different color here for fun. Let's do the smaller. You see that little side, x minus 1? X minus 1 over what? Over the 1 is equal to, y'all see what it would be? 1 over what? X, right? Everyone see that? Cool, let's cross multiply. You know, there's no division by 0. X is not 0. So x squared minus x, right? And I'm going to cross multiply equals 1. Hey, we have a quadratic equation. There's no reason we should not be able to solve it after, for example, watching like multiple videos of mine for solving quadratic equations, right? Anyway, so x squared minus x minus 1 is equal to 0. This is standard form. We're going to do, of course, this is not factoring nicely. You can probably see that. So by the quadratic formula, and I'll write that. Usually I wouldn't write that, as we probably know and understand it. But quadratic formula, a is equal to 1, b is equal to negative 1, c is equal to negative 1, right? And so you're going to put in, and you get x is equal to negative of the b, so positive 1, plus or minus the square root of negative b, b squared is negative 1 squared is 1, minus 4 times a 1 times a negative 1 for c, ac, right? All over 2a, 2 times 1. That's equal to 1 plus or minus the square root of, oh, that's 5 over 2. Now, x is positive, so because x, since x is positive, x is equal to 1 plus the square root of 5 over 2, which is actually, everybody, the golden ratio. So quietly I'll write here the golden ratio. And so even here, people don't always know that this is also here relevant, the golden ratio. And if you know what is what is cosine of 36 degrees, for example, it's actually equal to 1 plus root 5 over, remember that, over 2, x over 2, over 4. Cool. And you can do other, other things like sine and all that. Let me make it a little neater of a cool. Okay. So anyway, let's go to Fibonacci numbers. That's what kind of the title of the talk, right? So the title of the presentation. Okay, let me tell you Fibonacci numbers. Let's actually start with a0 equals 1. These are just, it's a sequence of numbers. Fibonacci sequence. Okay. And you start with a1, a0 is 1, and a1 is 1. Okay. And every other number is a sum of the number an plus 1 is the sum of the prior two numbers, the previous two numbers. A sub n plus 1 is equal to a sub n plus a sub n minus 1. Okay, and so basically the third number is the sum of the first two, the fourth is the second and third added, the fifth is the third and fourth. So for example, look, what's a2 equal to? 1 plus 1 is 2. A3, you're going to add up 1 plus 2, right? That's 3. The next one is 2 plus 3 is going to be, A4 is equal to 5, and A5 is equal to 8, and A6 is equal to 13. But here is where I want to show you how do you, where is it approaching the ratio of these golden, what is this golden ratio and how does it have to do with it? The golden ratio basically is, let's look at what the ratio of two consecutive numbers, Fibonacci numbers ratio is approaching, right? Is approaching. So it's going to be, you can see there's a pattern, it's like 1.6 whatever, and watch this. So, you have 1 over 1, 2 over 1, 3 over 2, 5 over 3. So in other words, like you have these, the next over the one before it. This is 2 over 1, this is 3 over 2, 5 over 3, what is that, 8 over 5, 13 over 8. That's what I'm trying to get at. And then what is this, 21 over 13, 34 over 21, 55 over 34, 89 over 55, 144 over 89, and so on and so forth. That's his idea. And we're going to approach this thing called, let me write it like this. Let me just call it x, for example, And so we're approaching x, and let's see what x will be. Now, here's the thing. The idea being that we want x is equal to basically the limit of these Fibonacci numbers, let's say n goes to infinity, right, of an plus 1 over an, and that's going to equal to what? Limit as n goes to infinity. And what is an plus 1? It's going to be an plus a sub n minus 1, right, over an. And by the way, shouldn't that also equal to, I mean, just change it a little bit, limit as n goes to infinity. Let's do an over an minus 1, for example, right? Let's look at that for just a second, okay? Now, right, because I mean, just n, I mean, you add 1 to it, it doesn't change that. It's infinity plus 1 is infinity, right? Now, look at this here. Here, this, and that. So they're basically, if they're approaching something, ultimately they're going to be very, very close, if not equal. You know, this one and that one, these numbers. So let's look at that. What if we did say, like hypothetically, that we're interested in kind of figuring this out right here? What is this? Let's look at that for a moment over here. Okay. What is that? And plus minus 1. Actually, even without having to write that much, let's see. Yeah, we can do that. Okay, so over an minus 1, right? And what I see here is, so it's approaching this number x, right? Just like an plus 1 over an is. And so if this is x, pretend that's x, right? We have, let's simplify this. This is what? This is, if you divide it, it's an over an, or separate the fraction, over an plus minus 1 over an sub n, which is equal to 1 plus, that's actually 1 over x, right? And that should equal to x. Wow, okay, that's just some kind of, we just got a quadratic equation. Look. So you solve for this. What is this? X squared. Let me actually just multiply both sides by x and keep it a little slow down for us. X plus 1 is equal to x squared, right? Multiply everything by x. X is not 0. So we have, what is this? X squared minus x minus 1 equals 0, which we have just solved above, everyone. And we have gotten, so x is equal to, solved above, for another problem, x is equal to 1 plus root 5 over 2, the golden ratio. Okay, and if you want to know even something cooler, but this is a little tougher and different in a sense to prove it, I believe that the nth Fibonacci number, a sub n, I may be off on a number, I'm not sure, maybe I'm not actually, but it's 1 over root 5, and then you do 1 plus root 5 over 2 to the n power, plus 1 minus root 5 over 2 to the n power. So if nothing else, it's going to be close to that. I actually maybe, I shouldn't be saying it because definitely I'm not sure, I forgot. Let me try some numbers, okay, just for fun. Finish this video off, just why not. So let's do this here. Let's do some numbers. Okay, so if a sub 0, I want to I wouldn't be sure what the numbers are. So 1 over root 5, and if you take it to the 0th power, it's, well, that's not helping, right? Because it's, let me see. Let me try without the 1 over root 5 first for a moment. Maybe 1 over root 5 to the n power. I think it's like this maybe, so to the n power 2. So if it's that, let me try it. That's going to go to 1, right? Because any of the 0th power is 1. So 1 over 1, and that's going to be 1 plus 1. That's a 2. Yeah, something's off. I forget this formula a little bit. Let me try just, sorry, I forgot this. So, and I can't really look it up right now because it's going to destroy the video. But anyway, to prove it is a little tough, okay, everyone? But let's just check out these terms, what this is equal to, and maybe that will help. So I'm going to erase this. I just want to look at this pattern for a moment. So let's say we have Bn is equal to this. B0 will be equal to 2 here, right? B1 will equal to, we can kind of do it for ourselves inductively a little bit, right? B1 is 1, this will be a 1. You see that? Because 1/2 plus a half, this stuff cancels, right? And the zeros just gave us a 2. That's gonna, oh, yeah, it's kind of weird. All right. Maybe it's not over 2 to the power. Let's see. Okay, what's B2? Let's check it out real fast. So it's going to be 6 plus 2 root 5 over 4 plus 6 minus 2 root 5 over 4, right? Well, that's equal to 3. Kind of out of order. All right, well, let me try B3. And I know how to do, it's getting messier. So something's off. I forgot a formula for it. There's a very similar, you do that and you'll get a Fibonacci number, then to 1. But anyway, everyone, I was just going to, we can play around with that, but we don't have much time. I want to just call it here, the video. Let me just do one more. B3 is 1 plus root 5 over 2 cubed plus 1 minus root 5 over 2 cubed. Let's just say what that is. That's going to be 1/8, and that's what do we have? That's going to be 1 plus 1 is 2. I'm just doing like the right and left side at the same time. Plus, it's 3, so it's going to be 6 times 5, because it's going to be 5 squared, 3 times, and that's it. That's the other stuff cancels. What is that? That's equal to 4. Huh. All right. Right? I'm kind of messing around here. All right. B4. I mean, well, let's do one more. That's kind of cool if I can do that, It's kind of, there it is. Is 1 plus root 5 over 2. Forgot this. It's a cool formula. 4 plus 1 minus root 5 over 2 to the 4. Let's just do that than last time. So this is going to be a little trickier. 1/16. Okay. So, okay, let me just kind of, okay, 1, 4, 6, 4, 1, right? So the middle term, what cancels? 1, 4, 6, 4, 1. So this is 1, this is a 1 minus 4 plus 6 minus 4 plus 1. And there's everything kind of going on. Is it, yeah, does anything cancel? I think the middle terms cancel. So 1/64 is what we care about. I think that middle stuff cancels. I'm not sure though yet. So yeah, it will cancel. And this is minus. Okay, so we'll do 1 plus 1 to the 4th plus 1 to the 4th is 2 plus 1/6. And then the last terms is going to be 2 times 5, right? And the middle term is going to be plus a 6. That squared and that squared times 5. And that's actually 25, right? Root 5 to the 4th power. 2 times 25. Yep. So that's kind of faster. It's fast and a little risky to do that quickly. 30 plus 2, 32 plus 50. I messed up somewhere. So what is that? 16 for sure, but 1 plus 1. Oh, that's just going to be not a 6. That's going to be just a what? There are 2 of those. 25, 25. Yeah, it's 2 25s, 2 1s. And the middle one's going to be 6 times 5, isn't it? What is it? 82 though. That's not good. Why is it 82? All right, let's not give up. This is something that should be a nice number. Here, 1 second. So 1/16. Okay, 1 plus, so plus a 6. That squared times 5 plus 25. And the middle terms cancel. So 1 plus a 1 plus, so 6. This squared 6 times 5 plus 25. Really didn't work out. Let's see. 26 and 30. Oh, there are 2 30s. I forgot that. Okay. So it's going to be 1/16 of 50 plus 60. 102, is it? 7. Oh, 112. Oops. 30 plus, what is that? 50. Yeah, 112, which is 7. That's cool. All right, that's actually not impossible. B5. Okay, I'm going to do the last one just for fun. I'm just messing around here, everybody. I know I shouldn't be doing this, but let me do it. Mathematicians like messing around. So if I want to compute this quickly, let me show you a trick. I can do this. The coefficients, remember the kind of the binomial expansion, it's going to be 1, 5, 10, 10, 5, 1. Okay, and the other one, 1 minus 5 plus 10, minus 10, and minus 1. So I'm going to talk about this doubling, and that doubling. 1, 10, 5. where this is going to be the x to the fifth, x to the cubed y squared, and x to the y to the fourth, okay? And I'm doubling that because there's 2 times I'm adding it. So it's equal to, and 1 over 32, right, 1/2 to the fifth. I'm just going to write 2 over 32, so that's actually 1 over 16, but let me just write that so you can see that's something. I'm going fast here. And this is going to be, okay, just doing x to the fifth, that's a 1, plus 10x cubed, so 10 times 1 times y squared is 5, okay? I already doubled everything, and then plus a 5 times x times y to the fourth is 25, right? Root 5 to the fourth is 25. And that's equal to 1/16 times, that's 151 plus, what is that, 125. That's going to be 1/16 over, I hope I didn't mess it up, 176. Probably kind of messed it up, right? Oh, that's 11. Dude, these are cool numbers, right, everyone? I just don't see a pattern with 2, 1, 3, 4, 7, 11. Maybe there should be a minus sign right here. You know, if we did a minus sign, everything would be amazing and awesome, but we didn't. So here is my question to you. This sequence of numbers, what is it? How about that? Let's leave it there. All right, have an amazing day, everyone.